So in the last lecture, I talked about the random walk converted to the quantum language, and with specific examples of one-dimensional geometry and the discrete evolution steps. It came out that the dynamics split into two modes. One of them was going to the left, other one is going to the right. And I mentioned that this behavior is connected with relativity, and it automatically comes in when you impose the constraint of unitarity. I would say a little bit more about it just to clarify. Of course, if you don't know anything about relativity, you will have to learn some basic things about the dispersion relations and how they change between the non-relativistic system and the relativistic system, and what are the solutions in terms of energies, etc. So I will just briefly write them down. So one situation was this diffusion, which had the just dimensional counting gave omega proportional to k square, and if you plot it, it will have a parabolic structure, and that is the well-known description of kinetic energy in a non-relativistic system. But then there is a picture of wave dynamics where, following the convention that the energy is always considered positive, you end up a dispersion relation which is omega is absolute value of k. And now if you just draw a graph, this is what it will look like. And the point of difference is what happens at the origin. Relativity produces a conical singularity. It generalizes to any higher dimension. 2 dimension, they will just look like a line. In higher dimension, it will become a cone. And this is seen not only in what we call free particle dynamics at high momenta in field theory or particularly particle physics, but even in systems like graphene, you end up with a dispersion relation which has this kind of property. Okay? And that is a signature of relativity. In particular, these two branches are not smoothly connected. There is something happening here which is a jump. And these two branches can be connected to the two propagating modes, which I discussed last time. One goes to right, the other goes to the left. Momentum has opposite signs, but energy is the same. Okay, so this and this is and these modes, if you literally now go into the language of quantum field theory, they get associated with what are called particles and antiparticles. Now, without going into the full-fledged language of quantum field theory, I can't explain the exact correspondence, but particles and antiparticles, as they are defined in simple terms, they are the copies of each other where all the physical properties are opposite, like charges, but the energies or the mass is identical. And there are various ways of how they can be included in quantum field theory, and I will only give some words. That antiparticles are more commonly used language in condensed matter system is actually holes. Both these labels are actually something which Dirac constructed when he constructed relativistic quantum theory, but they are used in now completely different contexts. When people doing particle physics, they will always use antiparticle, they will not use that terminology anymore. People working with condensed matter physics, they will talk about particles and holes. And this is probably something which is there in many of these textbooks. It's strictly not equivalent to that, but let me just explain it, that you have energy bands in solids, and some states are occupied and some states are not occupied, and in between there is a so-called Fermi level. So what does hole mean? Hole means that you take out one electron from the occupied levels and put it up there on the unoccupied level. So then you have actually a pair, an electron in the energy above the Fermi level and the missing electron in the energy below the Fermi level. Now, with the reference to the Fermi level, what the textbooks will explain is that a missing energy has all the opposite, or not the missing energy level of that electron has all the opposite property. So it will behave as if it's a object with a positive charge. So absence of an electron becomes a presence of a hole, and the presence of a hole now is going to behave as if it's a positive charge, and it will move around with particular level, but literally speaking, in the actual material, it is the absence of an electron. We just invented a new name for it, call it a hole. And that is one way of interpreting what this antiparticles and hole is, that they are missing states of negative energy. And the missing is basically something which flips all the signs of whatever that energy state is supposed to be. That is how it gets all the opposite property, and you talk about it. And the particle physics have a different language, and they are particles which move backward in space-time. Okay. This is something which we are not accustomed to, but it is a mathematical statement which is equivalent to the description connected with the fact that the propagation phase, which we write down either in terms of energy or in terms of the frequency, the convention is e raised to I omega t, and you wanted all the positive energy, it behaves in a particular way. Now you want to talk about a missing negative energy particle. What do? You convert it to a present positive energy particle and take the sign inside t. Okay, it's a jugglery, but you can do it, and then it will look like a positive energy object moving backward in time. And that is how particle physicists label this antiparticle. And literally that sign flip is all that is happening between the two components of the evolution, one going forward in one direction and one going backward. Well, the backward is what you can say that it's going back in time. You can label it in a very different way. It's a forward particle going back in time. This is the connection, but it's something which is present. You understand it in more detail. You have to worry about the whole language of quantum field theory, which I'm not going into, but I'm just emphasizing that this feature of wave dynamics is connected to the existence of antiparticle, which comes automatically from the quadratic dispersion relation, which is something buried inside here. There are two solutions which are written in the particle language, two signs in front of the square root, and so there is a positive energy and the negative energy, and you juggle around them in some way, whichever way you want. Either you talk about negative energy, but nobody likes to talk about objects with a negative energy, so you change the sign and say the positive energy and going back in time. Okay, so this is just for the sake of illustration. I can't call it complete because you literally have to understand the relativity in more detail and combine it with quantum physics to go further. Okay. This? This vortex? It's just a singularity. That the derivative is discontinuous here. It's continuous in terms of the function, but the derivative doesn't exist. And derivative is connected to the velocity. It is going to be discontinuous. On one side positive, on the other side is negative. So now I want to go further and ask, we constructed this classical random walk and its quantum analog, you can call it quantum walk. What is it useful for? We have to now bring in some problem which this particular structure can solve. And these are some of the applications. Either it's a random walk or quantum walk, and they will all be connected to a situation where there is a distribution in space and you are trying to move around, going from one location to another. So these are all distributed structures. You can represent them by graphs, and on this structures you will want to understand what you call propagation, and can invent some words for spread, for example, is another label, etc. And in terms of physics, this kind of criteria are connected to what we call kinetic energy. It moves things around in space. Now to go further, we can add in this dynamical problem what can be called a potential energy. And then together with kinetic energy and potential energy, we will be able to define various type of problems. Of course, what problem it will be will depend also on the details of what potential energy you add. There is not a single choice. You can have many different situations. Kinetic energy is very common in all problems of many different categories, and the generic operator for that is the Laplacian. That is what we constructed using random walk. But this can have many different functional forms. So this is a problem specific. And the simplest problems have some labels which can be characterized as a you can call it a spreading time. Another word which is used is a hitting time. Basically, you are going around in a larger space. These are measures of how fast you are moving. Okay. And they generically have quadratic speed up. That is some simple thing which I mentioned just by power counting, that how fast you are moving, the relations are very different. In Brownian motion, you have the distance proportional to square root of time, which is this situation, and in here the distance is proportional to time. So how fast you are moving, there is a change. And it's a quadratic scenario, and generically it will show up in problems which you construct without worrying too much about the details. But if you cook up some specific problems, you can have even more drastic behavior. It's kind of interesting that the speed up, which is a difference between these two, is the same as what is available in Grover's search algorithm. The Grover search algorithm has no connection to this behavior at all, but both of them give quadratic speedups. Okay, so I'm going to give a first kind of artificially constructed example, but there is a large change between the classical and the quantum version, and that is kind of instructive that unusual things can happen. And the example is something from work of Farhi and Gutmann. And they constructed a graph, which is a binary tree connected to each other in a particular fashion. So let me draw the graph, because it's a binary tree. So every step, there are two branches, and we keep on going. Number of steps, and let me kind of go one more level on top of this. So some situation where the number of points are going to double at every step. So 1 here, 2 here, 4 here, 8 here, etc., etc. And yeah. And what did they do for such a graph? That one of them is spreading out, the other half they made it contract, just a directly opposite manner. So it's nothing but mirror image. Okay. And the question is, suppose you start at this particular point. What is the probability or likelihood, or how fast you are going to reach the other end? Okay, so let me tell you that this is some number of levels. So let me call it n bifurcations from this point, and another n to go over this step. So the distance between this and this by following the graph is 2n, just counting the number of steps you need. But now you will ask what will happen when to go from one point to its neighbors. I use the classical walk, and in another case I use the quantum walk. Okay. So, okay, let me do some counting as well. So, how many points are there in the graph? So, the left half will be 1 plus 2, and this will become 2 raised to n in the middle. And here it is 2 raised to n minus 1 going back to 1. And we can add up, this is a number of vertices. It's a simple geometric series you can add up, so it's 2 raised to n plus 1 minus 1, and this is 2 raised to n minus 1. So the number of vertices on the graph is exponentially linear. And the distance you have to travel in a directed fashion is 2 times n. So distance and when I phrase the question that I'm starting here and I want to reach there, it is sometimes used with this label, hitting time. How? Because obviously I will need 2n time steps. Before that I can never reach that. But for time steps which are larger than 2n, what is the probability that I am able to reach that particular point? And remember, this is a random walk, so if any point you are here, you will have a probability that you will go to all its neighbors with equal chance. That is the structure of the Laplacian, and that is what we will use. So at each vertex equal probability to go to all its neighbors this is a what you call regular graph property. The graph is not fully regular because it will have 3 neighbors at most of the points, but this end point has only 2 neighbors, and this middle line also has only 2 neighbors. But we'll assume that this property is kind of true, and this n will be large enough, so hoping that whatever happens in this one or and time slice doesn't affect the behavior very much. Okay. Fine. So now we can construct the first the classical version. Where the generic solution for diffusion is an exponentially decaying process as a function of this is time steps, and this is a single evolution. It's a first order equation. d phi by dt is equal to something that is structure, and the diffusion equation has general solutions which can be written as exponential of some matrix, and this matrix will be positive, in the sense all the eigenvalues will be positive, so the solution will decay starting from wherever you are. It's a transition matrix in some sense. So what is the property of the single evolution? So this is a Laplacian structure. Where this H is equal to some value I have to take that I am at one point. I go in all the possible directions with equal likelihood. So I will give some value G. Okay, I have to give some index. So I and j, let them be the indices corresponding to the vertices. So the vertices are so many of them, and you are going to move on that particular graph. So this is if I, j are neighbors. And I have to conserve the probabilities, so I will have to put plus 3g if I equal to j for all the graphs except equal to 2g for I have to give some labels. So let me call this 0. There are two of them, and I will be the time slice, not some time slice, the graph slice of this particular problem. So if it is I equal to 0 and n is the middle. Okay. So this has a Laplacian. It just says that I take some population from this point and I distribute it equally over all the neighbors. That is what these values will do. J is another index for the vertex. Not to confuse, let me put another index over here. Okay, this is graph slice label, which is just a generic thing. And if this graph vertices are such that one of them lands up over here, then I have to use a little different normalization. But these I and j are vertex labels. Okay. And of course, there are lots of pairs where there is no connection. They are not neighbors, so they are all zeros.
Here, every vertex has 3 neighbors. No?
Except these endpoints. Okay. So now we can ask. We have identified the operator, which is a generalization of Laplacian onto this discrete graph. And the evolution equation is going to produce this. And in principle, you find a solution if you can diagonalize this matrix and find its eigenvalues. That is basically the final result, because you will get e raised to minus some lambda t, and lambda will tell you how fast you are moving. There is nothing more complicated than that, but that requires some amount of algebraic work, which it can be done, but it doesn't give you much intuition. Okay.
So this construction seems to be a little bit bidirectional.
Yeah, so if you are here, you will have twice the probability to go forward and once the probability of going back, and those probabilities will be reversed over here. So I can write down left half two-third probability to move right, and 1/3 let me just call it forward towards the target, and these numbers are reversed. And this reversal is actually what makes the problem hard, in the sense that if you are land up over here, it's much more likely that you will go back instead of proceeding towards the target. Okay. So, well, it can be solved exactly by diagonalizing this Hamiltonian. It is, in some sense, what is called a tridiagonal matrix. There is a diagonal entry, and one side is the positive forward neighbor, one side is a backward neighbor, and make a list and solve it. Numerically, it can be done, even if it cannot be written a closed analytical form. But I will give a more intuitive description, which doesn't solve the problem, but it gives a bound. And the bound is kind of good enough. Okay. It is just a change in the population which you are describing. This is the kind of equation which we had. This time derivative describes the change in the population. Okay, phi is the population. And what this Hamiltonian is doing is reducing the value of phi at that location and putting it on the neighboring points. Now, to get the positive signs correct, I have put a minus thing in over here. So this minus is actually responsible for what signs I put it over here. If I put a plus sign up here, then this plus g and this will become minus 3g. It's just a convention, but we want the solution to be well behaved, so it decays in time. That is a convention which we follow, and then this transition matrix will have this particular convention. Okay, so let me just do a simple-minded counting that up to t equal to or t less than 2n, no probability at target. You have started here, there is no way you are going to reach there if the time is not equal to the distance. What happens at t equal to 2n? You will exactly have the first possibility to reach over to the other side, but then you have to count the probability at every step. What is the probability that you are monotonically going on the other side? So there is a probability is in this particular half, it will give 2/3 to the power n, and on this half 1/3 to the power n. No, there are just exactly every step you take. I'm counting. Oh, you mean these endpoints? I'm not worrying about too much about endpoints. Okay, that is ignore. There are small corrections from endpoints, so ignored. I will say that. Doesn't change things that drastically. And this can be written as it's exponentially small in n. Now you ask what happens for t greater than 2n. Okay, you will still have some path which will reach there. Okay, there is one more twist, that this graph is something which is called a bipartite graph. Bipartite graph means that any particular slice will, some value of n will connect to the neighboring slice, which is n plus 1 or n minus 1. And the consequence of that is that you will exactly end up at this point only when t is even. If t is odd, there is no path you can write which will reach there. So we'll put that also aside. We'll consider only even t. Okay. That is fine. And now ask which is the kind of path which will reach the other side. So all of them will have a structure which goes forward. Some stage there is a backward step, and then it lands up on the other side. Okay. So this is for one kink for t equal to 2n plus 2. That's the only way you can reach there. You have to somewhere stall for a little bit so that you end up at the right point. If you want to go to t equal to 2n plus 4, you will do something like this. So the two kinks. And so we'll give a explicit sum over this whole series, which will give us a probability to reach the target at any time after t equal to 2n. Meaning summing up all the series. So I will now have to calculate what that series will produce, and I will follow this simplification, forget about this little bit of change of weights at the end points or at the middle point. And so what are these terms? So the first term is just this plus second term will have one kink, which will have one forward and one backward propagation anywhere, doesn't matter, but that will give a extra factor. So yeah, this will be a common factor. So let me just count the extra factors produced by the kink, which will be another 2/9, one forward and one backward is 2/3 and 1/3 multiplied together. But it can occur at many different places. So how many places? Well, the length of the whole series, which is 2n. And now we can try to make a simplification for all these pictures. Don't have to worry too much about exact values, but when I have two kinks, these factors will get squared. But on the other hand, these two kinks are indistinguishable. So I have to put a 2 factorial in the denominator. And then, well, I can assume that, yeah, it will continue. But the point of putting this factorial is to recognize that this is going to produce an exponential. Okay. So what is that exponential? Well, it is e raised to this term, which is 4n by 9.
If one thing occurs in the first part and the other thing occurs in the second part, aren't those both distinguishable because
This backward and forward points are it's the same point. Either both of them are here or both of them are here, and they will.
in the second,
Yeah.
one can happen in the first,
Yeah. So if it happens on the first side, the backward will be 1/3 and extra forward will be 2/3. If it occurs in the second one, the backward will be 2/3, the forward will be 1/3. The product. Huh?
Those two are distinguishable, right? Because the properties are.
No, they are not distinguishable, because what you are counting is this path, and this is just a location of the kink.
So, first selecting the position of vertex for these kinks, we have 2n possibilities. So for first kink we have 2n, but for the second kink probably we have 2n minus 1 possibility.
I'm going to ignore all this little bit endpoint that this can be 2n, that can be 2n minus 1. I don't particularly care where n is large.
But we are doing summation for increasing number of kinks. For large number of kinks,
It's going to be a bound. This is actually an overestimate. If you want to write it as 2n times 2n minus 1, it is a smaller number. You can do it at the same location also. That's not a problem. No, what he's pointing out is right. You can have a double kink, one on top of each other also. Nothing wrong with it.
What exactly do we mean by distinguishable? What exactly do we mean by distinguishable?
The kink occurs at some time slice, which I have labeled it at k. And it doesn't matter which value of k you are using. As long as the kink is at that point, and now you have to count the number of possibilities, the way this occurs. This occurs at one value of k, this occurs at another value of k, and the description is identical because the kinks are something which we counted, but as far as the overall evaluation is concerned, they are completely equivalent. So now, well, let me write everything as a function. There is a power. So I will make everything four over 9. What is the value of this stuff? Okay. And you can very easily understand that this stuff is less than 1. It's some power. You can write it as 4 by 9. Put e to the 4 by 9. The number here is less than 1. It can make much tighter bound, but doesn't matter. This is less than half, and square root of e less than 2. So whatever is here is less than 1, and so this is a bound. So that tells you that probability to reach at any time, we summed up the whole series, has exponentially small value. And why did it occur? Well, all this behavior of making this propagation in forward direction in this particular graph, very unlikely. It became 1/3 while it was 2/3 on the other side. And yeah, so and the purpose of cooking up this graph was to show that now if you do this thing quantum dynamics, you will get a polynomial probability. What exactly the numbers are don't matter too much, but exponential versus a polynomial is a huge change. Okay, so now this is a classical version, quantum version. So automatically thing which we consider is multiple possibilities are superposed. The description can still be given, but it says that if you are at this particular point, at the next time step, you will be in a superposition of this with equal likelihood. That's the only change which brings about. But now observe a particular pattern that whatever distribution will be produced, you start here. The next step will either some probability will still at the same thing, or some probability you will have equal superposition on these points. Next step, you will have either equal superposition here, here, or all the possibilities over here. So the states which will appear in the quantum evolution will be always equal superposition of different values of k. You can't have anything else. So at any and that is Hilbert space, which is much smaller, essentially a straight line indexed by k. You are not going to get any other state.
So are we saying that states on a level k are in equal superposition or like k's are in equal superposition?
No, all the states with the same values of k will have equal superposition. All the states, I can write it differently. They will all be equally superposed for all the values of k. And so the evolution is going to be in this much smaller dimensional space, which is essentially the distance between the 2 points. And that is the property which makes the whole difference. Here you are writing some evolution over number of vertices, which was exponential in n, and corresponding matrix, whatever it is. Here the structure is much simpler.
Why 2n plus 1 dimensional? Why not 2n?
How many values of k are there?
2n plus 1.
And so I will define that, well, whatever it is, the states, let me just call state k is equal to some notation I have to cook up 1 over n normalization how many states will be in notation of k. It's not going to be this, depending on which level of the graph. Okay, I have to cook up some convention. To be little bit more accurate. Well, I'll just write it in a simpler way, not. Everything which is in this particular column. Okay. And depending on how many of these things are, there is some normalization I have to put, and this value is can write down simple convention. So it is 2 raised to k on the first half and 2 raised to 2n minus k. So this is k less than or equal to n, k greater than or equal to n. How many points are there in that particular column? And all the evolution is going to occur among these particular states. So now we do the same exercise. We want to find a transition matrix of this particular type, but not between the states I and j, which were vertex label, but between states of labels k, because these are the only ones which are going to be non-zero. So the transition by this h, I will put the, but these are now k labels, these are not vertex labels. And now I have to write down it will be this particular matrix element for the diagonal part, and here it will be I, no, okay, I was using what notation? I and j. Okay, so let me, this is the diagonal part and this is neighbors. I have to evaluate this. So this is ij neighbors and this is I equal to j. Okay. And the diagonal part is going to be the same, because all that is happening is putting in these states with some different normalization, but it's a diagonal term, so these two states are the same and they are normalized, so that gives us proportionality constant equal to 1, and that doesn't change anything. But here you have to be a little more careful that yes, the value was minus this g, but this I and j are going to be neighbors and they will have slightly different normalization between these points, because nk is going to be slightly different. Okay. And you put in values and you will realize that because they are neighbors, one of them is this one is going to be smaller by a factor of 2 compared to the other. Which one doesn't matter, but one of them is smaller than the other by a factor 2. So whatever normalization came in here, there will be an extra 1 over 2 sitting in the element, well actually 1 over square root 2 because this normalization root 2 inside it. So this number turns out to be minus root 2 times g.
Diagonal term means we are not changing vertex. It is
Yeah. So here these are already properly normalized, but in this particular case, the two normalizations are different.
but in the dynamics, we were supposed to change the vertex position in 3 different neighbors, not into itself.
Well, it was all buried about the definition of Laplacian. There is some probability to move and some probability to not move as well.
In
That is included in this analysis.
But in classical analysis, 1/3 probability to move and 2/3 probability to move forward. In that sense,
The value of g will decide how frequently you want to move, and you can tune it to whatever value which is allowed by the rules of probability. But in general, I can take a situation where by taking g going to 0, the Laplacian will go to a limit where there is no movement at all. See, this is a diagonal part of the Hamiltonian which will correspond to identity operator.
And suppose if we put k is there,
Hmm?
suppose if we put k is there, which is appear in the middle of the tree, then we'll have 2 power n by 2 basis vectors, right? In that expression.
Here, yeah, this normalization will have slightly different values for endpoints and things like that.
Just when the k vector is, when we expand the k vector, suppose k is there,
Yeah.
then the i's there are basis vectors.
However many are there in that particular slice, you have to count.
If k is n, then 2
And those numbers are here. How many are there in that slice?
then wouldn't the Hilbert space be 2 power n?
Hilbert space is just number of time slices because all the values for a particular fixed value of k will always have the same probability or amplitude in this particular case. So all you need to do to count this, how many different values of k are there, and those numbers are 2n plus 1. The states in the same column cannot be distinguished. The Hamiltonian does not distinguish them. Okay. So this stuff looks very similar to what is over here. Some overall numbers change, doesn't matter much. What has drastically changed is the dimension of the Hilbert space. That this is a there is evolution along a line labeled by values of k. And that is a huge reduction compared to the dimensionality of the matrix, which was here 2 raised to n. And the solution, again, you can work it out in great detail, by taking that Hamiltonian and I can diagonalize it. All you have to do to find eigenvalues, well, you can do it. It's not that much of a trouble, but we know what happens in a one-dimensional revolution with this probability of moving back and forth. That is effectively the kind of scenario I dealt with in the last lecture. Some transition element, some probability here, some probability moving back and forth. So in the language which I used last time, for this will have positive momentum, negative momentum, and some part which will just stay at the same place, which is in the relativistic language, the contribution of the mass. The mass term in the relativistic equation doesn't move. Plus and minus p move forward and backward. So this is what can be called a wave packet. The equation tells you that that wave packet sometimes goes here, sometimes goes here, sometimes stays at the same place. But what was the most important property of that wave packet? That wave packet moves at constant speed. That was the characteristic of the wave. Connected here, one side is speed is +1, the other side is -1, and that will just go in either direction. And so now that essentially tells you that behavior has changed drastically. The distance to travel is 2n from here to here, and you have a component which can move at constant speed. So it will hit the other part. This limit doesn't change because distance is same. You need at least, even with a constant speed, so many time steps to reach there. But behavior after this t becomes equal to 2n can change. So minimum but what we are interested in is just not the time, but some analog of this. What is the total probability which you can reach at that particular problem? And for that, well, this is a one-dimensional problem, and I have again not bothered too much about this end points and middle points where these values are going to be slightly different. The same way they were different over here because the number of neighbors are different. But ignoring all that, you can still find a reasonable solution. That exact solution actually can be obtained. So ignoring these endpoint solution comes out in terms of Bessel functions. Algebraically, these are all different identities, but one can easily understand how these things arises, because if I ignore the corrections, this is a one-dimensional problem and a tri-diagonal matrix. Okay. The main diagonal and the two plus or minus 1. And easiest way to solve them is Fourier transform the whole thing. So you have a matrix Hij where this k label are in position space. Go to momentum space. So then this produces a term which is identity, nothing much happens, but this back and forth produce term which is cosine of k. 1 unit back and 1 unit forward. If I write it Fourier transform. I need a Fourier label, so the coordinate label is k, so let me write it e raised to I p k. So then by Fourier transform it, this thing corresponds to difference of k between two values equal to 1. So it will produce a factor of e raised to ip. And the symmetric, so e raised to ip and e raised to minus ip will give cosine p, and that is a diagonal matrix in the p space. Because there will be cosine p, there is identity, and that is p space, it's just a simple function, you can invert it.
What is this P?
Hmm?
What is P?
P is the momentum corresponding to this mode k. K is a position or the slice coordinate.
This P is not the same for all K.
Hmm?
This P is not same for all values when you have K.
It's the variable conjugate to k when you use a Fourier transform. Whatever it is, I don't want to give it a new name, but when you Fourier transform from one variable, you go to the conjugate variable. Call it whatever you want. And the point is that this is a matrix of a simple structure that if you Fourier transform it, it becomes a diagonal matrix. And the important point which we need over here, what are the eigenvalues of the diagonal matrix? Diagonal elements, nothing more than that. And if you do that, then you calculate the whatever, that e raised to iht. So, okay, I have to write it down. So, I need a corresponding to this solution is e raised to iht compared to the diffusion equation, which was e raised to minus ht. This is a wave equation with there will be this I coming inside ht, and all you have to do is find the eigenvalues of h, and this Fourier transform will give you the result, and you can evaluate it explicitly, but the point is that just the properties of the Bessel function is enough to tell you what happens at some value of time. Okay. what we want is a behavior after t equal to 2n, and the answer, so for t greater than 2n, probability at target behaves like 1 over I think square root. That is from the explicit structure of the Bessel function, whatever it is. You can write down the asymptotic series. That is good enough. And if you look up any of these mathematical books, it will tell you that Bessel function of some argument z, there is a cosine and sine oscillating term, but in front of that there is a normalization. And or j of z, that normalization happens to be 1 over root z. And that is what I am putting inside here. That 1 over the square root of the normalization, it will come out over that. And if you write this integral sum over all the eigenvalues, that will give the total amplitude. That exactly produces the mathematical identity, which is one of the description of the Bessel function. Something like e raised to cosine t. So that is what this is going to become. Diagonalize h, it will become cosine p and t. So the integral is e raised to cosine p times t, summed over or integrated over all the values of p, and that is one of the definitions of the Bessel function. So that's how it comes, and you can solve for it. But the point is, this behavior is very different than this. Okay. It's a polynomial in n. This was exponentially suppressed in n. And so what they call this hitting time on this particular graph is exponentially improved compared to classical walk in the case of quantum dynamics. So, of course, this is a kind of cooked up example with some definite structure buried in the graph, but these kind of things are allowed by quantum theory, and that is something which needs to be well understood. More general situation is what I described here by just doing a little bit of power counting. Here, distance square root of time, distance proportional to time. So in some generic graph, not a particular example, there can be a quadratic improvement, but on specific instances, the improvement can be even more. And yeah, so I will stop in this problem at this particular stage, but in the next class, I want to take a more generic situation where we add some potential energy. Remember, this is only the kinetic energy part, how fast you are moving, nothing more than that. But you can create more elaborate problems by choosing some particular description of potential energy. And the problem which is easily connected to what I had done in the previous course is database search. I described the algorithm for Grover's solution, which was described in some abstract Hilbert space. But I can now ask the question that space is actually a distributed database. Something is here, something is there, something is there, and I want to run around and find what I want. So I have to propagate on a graph connecting all those points, and the limitation will be that one point will be connected only to its neighbors. If I take one point, I can say I can go anywhere from here to another location in one step. It becomes Grover's algorithm. The Grover's algorithm did not have any measure of distance between various Hilbert space components. Now I can put a restriction that the Hilbert space components are local. They can only go this far in one step, and I still have to find some item which could be anywhere in the database. So it will be a distributed database search with a locality constraint on the propagation. Of course, it will be slower than Grover's algorithm because Grover's algorithm could jump from anywhere to anywhere. Here you are putting a restriction. But the question is to then understand how much is the restriction and what are the physical principles which will be involved in that. So that is the target for the next class, distributed database search. So it will have this structure. And remember, Grover's algorithm had two operators. They were both reflection operators. One of them will represent the kinetic energy, but the other one will have to be mapped to potential energy. That is the target. I want to go to that particular location, so I will put an attractive potential in that place. So that when I'm moving around, if I fall into that particular location, I don't move out very easily. It's an attractive place. And on the other parts, not interesting, I will move around with van der Waals. So the oracle becomes potential. And we'll see what happens in that particular case. Yeah. It is still going to be a relativized problem in the sense that the oracle has to be supplied to you. It is some property of that particular target item which will identify it. You don't know a priori what that property is, but you just construct the algorithm saying that if I happen to hit that particular object, I will recognize it. Yeah, so that is the description of oracle, and I will map that to a potential energy. The potential energy of that particular location, it is constructed by that, whatever that property is.